Hello everybody. It's time for the afternoon session of the OSGi track. And before we're going to start off with the next presentation, I just want to mention again that don't forget to pick up your OSGi t-shirt. And at 6 o'clock tonight, it's going to be the 20th anniversary of OSGi. So make sure you're going to be, make sure you're there, and there's going to be cake. But now I'm going to hand over to Mary Grugleski from IBM, and she's going to be talking about streams in OSGi, I guess.
That's right, that's correct. Thank you. So yes, so let me do a quick introduction. I know it's only 30 minutes or so. So my name is Mary Grugleski. I'm an IBM developer advocate. And by night, I'm a community organizer. I help to run the Chicago Java Users Group and other IBM sponsor meetups in Chicago. So if you're ever in the area, please let me know. Come or do talking too. So yeah. So today my talk is about streams, and I name it Thirst-Quenching Streams for the reactive mind, because as such, streams are kind of becoming like the thing you do when you do reactive programming, because we're now dealing with data that come in as streams. But first of all, may I ask you who actually in here are already working with streams in one way or the other? Oh, cool. So like reactive platform systems libraries as well, presumably? Yeah, yeah, okay. And how about like what type of library? Like do you work with like Reactive Extensions, Spring Pivotal, or Akka? OSGi, actually, this is the stream. I'm sorry, Push Streams. Oh, okay, cool. Yeah, that's cool. So as such, too, I'm not. I'm kind of new to the Push Streams, and because I'm in a team of like experts that I work with at IBM, Dan, who is here, president, and BJ, who's the lead architect developer. So yeah, so that's why I'm like doing this talk is basically to do a bit of comparison of push streams and then versus reactive streams. I'm actually more familiar with reactive streams because I've been doing a lot of talks, or actually, yeah, a lot of talks, but primarily so far it's been mostly introductory type of talks and that touch on some reactive streams kind of concepts. So as such, I'll start. Actually, I'm so sorry, I forgot my clicker. So give me just 1 minute. I'll just quickly set that up. Just makes it easier, I think. Okay. Okay. So first of all, let me then talk a bit, because it seems like most of folks here maybe have not worked as much with reactive, and some of you just wanted to get a bit of an introduction. So I I hope it doesn't, you don't mind if those of you already are familiar with it. So first of all, just like to talk about a bit about reactive programming, and then reactive systems and reactive streams. So reactive programming itself is basically asynchronous programming that actually concerned with data streams and in the propagation of change. And that means that it becomes like possible to express like static or dynamic data streams with ease, like via the employed programming languages as well. I mean, as such too, it doesn't have to be Java, it can be any kind of languages too. And primarily too, it's dealing with event-driven programming streams, and there are no callbacks. And that's like the advantage too. If the old style of programming, we're dealing with like concurrent distributed systems, then we have to add in like locking and threads and all those. So that can become kind of messy, and also then you have to put in callbacks as such. So then the advantages of streams is that you eliminate that callback. And callback too, not just like in the callback, the mechanism, but also in how you deal with like this, the syntax of your program, your semantics too. And of course, one advantage too, like dealing with reactive programming here too, I kind of also have talked about reactive streams, and that's like a specification for dealing with reactive programming. But as such too, it's we're then like talking about because when data is coming in, then you have to like deal with the like back pressure that can build up, because the streams can be coming in and like continuously, and so you can actually have requests coming in that's faster than the consumer can handle it. Basically, upstream can coming in, the downstream may not be able to handle it on time. So that's why too, like there's the like reactive programming too, it's actually also handling the like back pressure aspect of it. And so another thing, like then when we talk about reactive too, we also like talk about reactive systems. So I like to also point out there are differences too between like reactive programming and reactive systems. Presumably, if some of you are new here, just want to point out. And reactive systems is basically dealing with system as a whole. So reactive programming itself is, say, dealing with one component, but reactive systems is basically you go up a level that you deal with systems as a whole. Then you can have many components, each of them like using mechanism of reactive programming to do its thing. But in order for the system to operate like in a very coherent fashion, then you basically are using reactive systems approach to do it. And that actually is basically is a higher level of asynchronous kind of aspect of your systems. And for those two, like with reactive systems too, you have like different kinds of patterns that handle, for example, like back pressure, like I mentioned about back pressure, or handling like circuit breaker, handling some of the data that's kind of coming in. They need to have consistent data, and they need to be highly responsive. And as such too, in today's world with reactive systems too, there's this one specification, or actually more like a manifesto. It's actually it's initiated by Lightbend. Over here is the Reactive Manifesto. So the Reactive Manifesto too is dealing with the 4 aspects of your systems, which has to be reactive, responsive, meaning that your response have to come back in an on-time fashion, and needs to be very elastic, scalable, so there are more requests coming in than your systems needs to scale properly, so then your throughput won't suffer. And then there's also recoverability aspect of it, the resiliency part of it too. It's also should be built into a reactive systems. And then everything is made possible by the message-driven capability within your system. And there are also differences too, by the way, too, between like event-driven and message-driven. Message-driven are dealing with two components, two pieces of your interaction within the same system. They have like fixed, the address of where your messages are going to. Whereas for event-driven, is basically more like a publish, subscribe type of situation in which your messages are being kind of broadcasted. It just doesn't know where it's going to. Whoever is interested in it, it's called observables in reactive extension terminology. It's basically you observe it. Like these are observables that are events that come in, and then there are observers that are observing these events coming in. So that's I would like to also point out as well. And then when it comes to Reactive Streams, Reactive Streams is basically an initiative. It provides a standard for managing like asynchronous stream processing with non-blocking back pressure. And the effort too is aimed at not just with Java or JVM, but like any other like networking layer too. And also, as such too, you can have runtime environments that's JVM or like JavaScript as well, and potentially other ones too. So that's that for some introduction of this. And here too, let's also talk a bit too about the problems we are trying to solve here. I mean, why reactive, right? All of a sudden, like we have all these reactive kind of terminologies popping up, and the reason is that it's systems becoming more sophisticated now. We have to handle is essentially concurrency and distributed systems, large amounts of data. For example, IoT applications, the devices are continuously sending data over. So in order to efficiently process them, you basically want to like handle like making your systems more able to operate in a like highly concurrent way, or like handling all your processing in parallel. But just want to also point out a bit too is the differences too between concurrency and parallel too. So concurrency is basically you're dealing with multiple tasks like all at once. You can actually have a single CPU too, that you can kind of set up threads and they all handle tasks concurrently. You start the task, but they are essentially, I mean, like behind the scenes, they are actually being handled one after the other if you have single CPU. But that's the thing too, like with parallel, then it's different because then you're doing like multiple tasks, you can doing them all at once. And that will actually require your systems to have like multi-core capability or multi-CPU. So then like, essentially you can have one task, but the task can be split up so that they each can be handled in parallel. They are being handled like all at once, and like maybe one part of it is being handled by this core or the other. So in some ways too, like right now it's the right time for doing reactive systems, because now with all of these advances in hardware, virtualization is making reactive systems all the more like important in today's world, and basically it's essentially software catching up to the hardware. And let me just also talk a bit too about streams processing too. So there are two models essentially of processing streams. Basically, they're push or like pull model, broadly speaking. So you can have like upstream basically pushes the data. I mean that by such saying push, it means like upstream like pushes the data to the downstream. And then for the pull, it's basically downstream will pulls data from the upstream. Now, as such too, like the push stream in OSGi, that's essentially is a push stream, very strictly like push stream kind of model, and it pushes data to the downstream. And the pull one is it's actually more like an implementation. That's the differences too between, as I'm studying, then the push stream essentially is a strictly push model, but the reactive streams as such is not, it only is a specification. It doesn't specify, you know, how you implement. It's up to service provider to implement that. But essentially, it uses a pull model primarily because, like, let's say I'll go into a couple slides. I will talk about reactive streams implementation, but as such, and that's the high-level differences. But here too, I'll just use a bit of like marble diagram too to explain a bit of stream processing, stream programming. So if you go, this one comes out of the reactive extension marble diagram. So we're talking about, when we talk about stream programming, we're like basically representing your streams like in timeline like this. So the top one is basically a stream that's waiting for events to happen. And then the second stream in here is basically there are events that are happening. And over here, there's like a perpendicular. It means that the stream has a definite time period to it, and it terminates at that point. And over here, too, this one is basically another stream, but you see an X, because this represents, the X represents an error event. So in any kind of reactive programming, it's basically error event is being treated as first-class citizen, too. So it's just like any other events. It comes in, but it's an error that needs to be handled. And the bottom one here is basically streams, but it's an open-ended streams. It's just continuously waiting for events to like listen for events to happen. So, okay, and here too is just a quick example, but I probably won't spend as much time, but just want to give a quick thing. So basically, if you and how do you basically transform the data that comes in on the stream? Is basically you use operator. So for a reactive extension, for example, you do like a map operators, and then it transforms it, and it's functional style. So you basically have streams of, like, say, carry data of 1, 2, 3, and you apply like a map operator to it, and you specify your transformation, and in this case, multiply by 10. Then you see the output over here is item 10, 2 becomes 20, and 3 becomes 30, like that. And that's just how you implement it. It's pretty clean, so. Okay, so now then I'll go into talking a bit then about the push streams. And so basically OSGi has the push stream release 7. And basically this is the package that comes with it, and it has a self-implementing API. So as such too, it doesn't have any dependency on the rest of the OSGi specifications and frameworks except for OSGi Promise. And basically, some common concepts about it is basically the API itself is inspired by the Streams API in Java 8. And it uses the basic concept. So you can reference like the Java 8 API too. And basically, I mentioned about that. And then it's also like it's built to handle asynchronously produced events. And also too, it handles back pressure as well. So the design provides a means to for the event pipelines, so it can communicate back pressure back to the source. So that has that capability. And also too, interestingly, so that's one difference too in the push stream, as I'm finding out, is that your consumer can then tell the source, the data source, that, well, I want to close this stream. So that's one thing that's different that I've found out, is that's in push stream. Whereas in reactive streams, it doesn't have such capability. Your consumer actually doesn't have any access to your source. So, but then for the push stream, it has this capability. And then basically too, they're also, one thing is the generified. So generics are basically used to promote type safety too in push streams. And the different entities in push streams will be the push event source. So push event source object basically represents the source of asynchronous events and can be used to create a push streams. And the consumer side, then you have a push event consumer, and it basically represents a sink for all of these asynchronous events. And they can be attached to a push event source or a push event stream. And the push stream object basically represents a pipeline for processing asynchronous events and their terminal operation. So final operation of a push stream pipeline basically results in a promise that I talked about earlier. So that's the only dependency it has on an OSGi specification is the promise. So that represents the completion state of the pipeline. So basically, if your pipeline coming in, collecting all the data, all your asynchronous processing, then all of these can go into this promise object, and then that's when your processing is all the data is in, then it's the promise that handles all of the data that you have collected during the call. So yeah. I'm sorry, my. Oh, the screen stopped. Oh. Oh, switching sides. Oh, okay. I'm sorry. Okay, yeah, but that's the next one. I was just mostly talking. Sorry. Yeah, I figure it's better to talk than put everything on the screen. So yeah, that's what I received too. Like for my feedback, they say, "Oh, don't put too many things." And so yeah, but thank you. I hope it makes sense. So, but yeah, but that's about what I was talking about. Just give you an introduction for those of you who were not familiar with push streams. So that's what push streams are like. And then now I go into reactive streams. So reactive streams basically has the OSGi Streams API. And essentially, it's only specifications, and it doesn't have any implementations that it specifies. It's up to the service provider to kind of define how they want to implement it. But the idea of such is that the big emphasis on it is on interoperability. Rather than saying how you do things, it's basically saying that, well, we need to have certain things and that type of stuff. And as such, reactive streams also has a TCK. So that will kind of certify that a service provider is actually following the spec. So, and over here too, I'm just going to talk about these 4 specific implementation libraries that implement reactive streams. And actually, in my original description of my talk, I didn't talk about this one thing, which is RSocket, because when I submitted the paper, it was before I knew about RSocket. And then during the time I'm preparing, I said, oh, there's this RSocket. So I started reading up, and it's very interesting. So I like to also point that out in here, for especially maybe some of you may be interested in that. So essentially, two reactive streams is implemented by Spring Reactor and Reactive Extension, the RX, and Akka Streams, and also RSocket. So I'll go into a little bit of each in the next set of slides. Just let me kind of first of all to mention too, Spring Reactor and Reactive Extension, they are kind of similar. And the reason is because the two teams working on Spring Reactor and also the Reactive Extension, they are the same team of folks working on it. So you can find that their APIs, the implementation is actually quite similar. So I just want to point that out to you too. And that I'm referring to Reactive Extension RxJava 2. The RxJava 1 is slightly older, and it doesn't have back pressure support. So, but I'm talking about RxJava 2. And Akka Streams is actually came from Lightbend. You might have heard of the company that's originally called TypeSafe, and they are based in Switzerland, Sweden or Switzerland, somewhere in Europe. But Martin Odersky, yeah, I'm sorry, I can never quite remember which one. But Martin Odersky, the Scala inventor, actually is one of the founders of Lightbend. So. And then RSocket is a most recent implementations of reactive streams, and I'll go a bit into details too, because I'm kind of getting excited about that as I'm kind of starting to do some talk on this too. Okay, so let's kind of first too, I talk about, and I'm sorry too if you don't like the purple, but actually I have it blue, it's the IBM blue, but for some reason when it translates, from these slides it becomes like purple. But so anyway, yeah, okay. So just wanted to talk a bit then first about Spring Reactor by Pivotal. So Reactor is really a fully non-blocking reactive programming foundation for the JVM. And it's very efficient, like demand management. That's what they claim, right? And it's managing back pressure, essentially. And it integrates directly with Java 8. It's actually came out of Java 8. So the interfaces are more cleaner than the RX, the Reactive Extension too. And we'll take a look. And so basically too, talking about which, with Reactive Streams too, like how when you do implementations too, you specify your source and then you do the transformation, like just now when I showed that one diagram, the marble diagram, then you do a subscribe. So in some ways, reactive, and that's something I'm also trying to figure out. I've read documentation that says reactive is a pull. Whereas if you go into reactive streams, they describe themselves as a push. But what I'm kind of reasoning with is that it's more like a push than pull, because, or actually I should say pull than push, because it's your consumer that basically subscribe to it. So the data won't be sent to you until you subscribe. So when you subscribe, then the data will get pushed to you. I think maybe that's what the reactive streams is meant to be. But so essentially too, I just want to point out, so that's how when you do Spring Reactor, Reactive Extension, you basically have the streams and then you do a subscribe. And that's when then data will start to be pushed to you like that. So, and I mean, unlike like push streams, it's a different model in which data will automatically be pushed kind of to you. Yeah, so. And so basically, too, what other thing? And okay, so that's that. And also, too, with Spring Reactor, too, they have the concept of basically come out of Reactor Core, the library, has this support of the web flux. It's basically you use either flux or mono. So flux is basically a 0 to n items in the stream. So you can actually you can say get some results, and the streams can come back as a flux. So that means you can have like multiple streams coming back. And then, or you can kind of do a mono, which actually is only 0 to 1 stream coming back from your core like that. So that's some implementations in how Spring, in a high level, that's how they do it. And now I kind of, because of interest of time, I kind of go straight into like reactive extensions, the RX. So RX is basically an that one actually came originally from Microsoft. It's the .NET, RX.NET that came out first, and then Netflix ported it to Java in 2013. And as such, too, they had released one earlier in 2013 or 14, and then 2016, then release 2 came out, and that's when also the Spring Reactor folks have worked on that version, and that one is called Flowable because it has back pressure support. So this is the link to their information if you want to get more information about that. And yeah, so over here I describe about that, and basically. I just wanted to describe. So in order to operate on your streams, you basically will have to use operators. You can create the observables or flowables, and then you can also transform it. So for example, like create, you can just do a .just from your observables like that, or flowable. And then you transform your observables using the example I had earlier was .map or .buffer or group scan, filter, those things. They are more like transforming the data in your stream. And then you can also combine the observables to using like zip or zip with or merge, those things, and you can also schedule them too. It's basically you can add thread support to it and switch your threads to using scheduler too. So that's how you do that for a reactive extension. Oops. Wait. Oops. Something's not working, but now by hand. Okay, so now let me then go into talking about Akka Streams. So Akka Streams is from Lightbend. So Akka Streams is interesting. They are kind of, the Lightbend folks are more academic in nature. So they are kind of trying to stay away from saying that, well, that's easy and intuitive. So they spend actually a lot of time to make their, or so they claim, right? They said that they will do things a lot simpler rather than sacrificing it for like ease of use and all that. So they actually, the way they do it is actually they implement the reactive streams, and they're focusing on like interoperability with other conformant specifications essentially. So they completely basically separate the reactive streams interfaces from the implementation from the user from the user level API, because they consider those to be like service provider interface. So they don't want to do it like that. So for example, like in reactive streams, it's basically, actually I'll go into the next few slides too. It will talk about there are essentially 4 interfaces. They're actually very simple to the reactive streams. They have like publisher, They have subscriber, and then they also have the streams. Actually, what was it? Which I'll go into, but they are essentially 4 interfaces. So for Akka, what they do is that they have a corresponding like sync.as publisher, and then also a sync.as subscriber element too that must be used, and that's what they specify how they do their the support of the reactive streams. Let's see. Okay, so, and they also too have specified it by, like, the materialization of Akka Streams is basically restricted to having only a single subscriber. So additional subscribers will be rejected because they believe that the stream topologies described using their domain service language will never require some fan-out behavior from the publisher side. So that's something too. If you want to go into it, you can look into their documentation. So they favor essentially the compositionality. So basically combine different pieces. So then, like, basically then you can retain all of the functions of each of the part, and that's how they do it. And then they also have tooling that handle all of the stream processing concerns like back pressure, buffering, and transformation too. Okay, so that's Akka Streams. And then now I get into talking about our socket. So our socket is actually a relatively new, not so new, but maybe over a year or so, kind of implementations. It's open source, and currently is really heavily actually supported by the Pivotal folks and also Netify, this company in California too. There are a bunch of people working on this implementation. And essentially our socket it implements the reactive streams, and it's a binary protocol for use on byte stream transports, such as like TCP. It can be like WebSocket and also Aeron too. Aeron is a layer 4 kind of UDP kind of transport. So so it's as such too. They are duplex too, and it's and supports all the async application communication, and they are binary in nature. So they aim at like reducing like hardware footprint. And basically, because the whole motivation of them is that they're looking at, like with reactive streams, like all these processing, basically there's a lot of latency issue that they are trying to kind of focus on solving. So they do so by doing this, it's on the layer 5 and 6 kind of layer to do this like implementation. And so they hope to like increase the CPU and memory efficiency, and also like through their binary encoding too. And they avoid like redundant work too. So then they allow kind of persistent connections too. And you can they actually have 4 models of like streams. It's basically you can have like one direction is you fire and forget. Your request comes and basically you don't expect a response. Or you fire once, so you expect one response to come back. Or you can also have like a bidirectional. Basically, it's a persistent kind of connection too, that you can have a duplex kind of connection to that too. So the idea is that they will avoid handshake. So then it will basically and the associated like round trip kind of network overhead. So they are pretty efficient in that sense too. And yeah, I guess for some reason my system is froze. Okay, well, okay. So I get to the next slide. So here too, this is a slide actually I borrowed from Pivotal too, and it's essentially about their support of our socket, and there's also a new foundation called Reactive Foundation, and this one is actually they just recently announced it in like maybe a month or so ago, and it's currently living under the Linux Foundation umbrella. So sorry about that. It's not Eclipse, maybe not yet, but anyway. So yeah, so these are the companies right now that kind of founding members too: Netify and Facebook, Alibaba and Lightbend, and Pivotal, and this company called vLingo too. So over here they are layer 5 and 6 communication protocol, and they're supposed to be 10 times faster than HTTP and using 90% less resources. And they have new capabilities like streaming, resumption, cancellations, all these. And without saying, the reactive has back pressure, flow control. And it's transport agnostic too, so you can run on different transport protocol as well. So it also has, it's actually a better choice than like say WebSocket over HTTP 2, which is they're thinking, okay, you can use that, or using gRPC and using protobuf. And so basically they claim themselves as like a better alternative of like doing like streams. Okay, so then let me then go back to a bit of comparison, back to the push streams versus like reactive streams. So all these talk. So essentially, too, reactive streams, as I mentioned, is only has like 4 interface. As such, they are just on interface specification level, so doesn't go into deep into how to do things. So and push streams. So if you compare this one's actually I borrowed too from Tim Wart's when I was doing research. So maybe some of you have kind of seen it before, but so basically Reactive Streams is based on Java 9. It has the data source is publisher. Push Streams has the push event source, and then Reactive Streams have subscriber, and Push Streams is push event consumer. And the connection will be a subscription on Reactive Streams, and whereas like Push Streams, again, it has the auto-closable part, which is kind of different from Reactive Streams. And then the pipeline is a processor for Reactive Streams, and Push Stream will be their pipeline specification or interface. So. Okay, so this one I already talked about too, because I think it looks like I have 2 minutes or so left. So Push Streams has the auto-closable, and Reactive Streams is really like a pull and then push kind of model, which I talked about already. So. Oh, I think then that's all I have at this point. I didn't know. I thought I had more too, maybe. So, but thank you very much. If you have any questions too, please, yeah, kind of reach out, and I'll be happy to discuss about further too, because I think this whole like streaming technology is kind of still new, still kind of forming in some sense. And because when we deal with concurrency and distributed systems, it's never an easy subject. It's kind of elusive. Even if I'm looking at it, I thought I knew, then the next day you come back, it seems like it's different because you get enlightened or have some new idea, and then something happens and you need to like try to like kind of think of new ways of how to solve problems. So yeah, so so I think actually it's at 3:45, right? So yeah, so I'm like 3 minutes earlier. So thank you very much for coming to my talk, and please give me any feedback, and I welcome your feedback, and thank you. So yeah.
Sorry? Yeah, we have like a couple of minutes, and it's cough afterwards, so I think I actually have plenty of time if you... So
Okay.
do we have any questions from the audience? Okay, thank you, Mary.
Okay, thank you. Thanks, thank you. Thank you. Yeah.